Hello again. We're going to look at some Simulink control examples in this tutorial. So in this section, 3 different methods for simulating a linear system with Simulink will be presented. These 3 methods are using transfer functions, using a state space representation or SSR, or the integrator blocks for each state variable equation. Note that we may use transfer function or an SSR only if the mathematical model consists of linear ordinary differential equations or ODEs. So we jump into the first example, that is example 6.4. Consider again the three-way spool valve system that we have worked with before. Simulate the system response using Simulink with a transfer function representation. The applied force Ft is a step function with a magnitude of 12 newtons. So here we have the spool valve or the three-way spool valve system again. So we have the spring, damper, mass, and an external force. So we have seen many times that the system model for this system is equal to my double dot plus by dot plus ky equals f of t, where y is the position from the equilibrium and ft is the electromotive force that is the input to the system. And this system is initially at rest, meaning the initial condition for this system is 0. So that means that we can actually use a transfer function to be able to simulate this system. We have also obtained the transfer function for this system using the system model. So doing that, as we recall, should give us the transfer function gs, that is the fraction ys over fs, or output over input, equals this fraction as 1 over ms squared plus bs plus k. Now we know for this system, as we have seen in the past, that the values of mass, damper, and spring constants are equal to m 0.04 kilogram, b 16 newton second per meter, and k 7,000 meters per meter. So with this, we should be able to have our transfer function. Now in the past, we have used this transfer function to make a simulation in MATLAB and get the system response and outputs. This time we want to see how we can do the same thing in Simulink and more visually. So for this system, the EM force is a 12 Newton step input that is steps up at t equals 0.02 seconds. So what do we do in Simulink? First of all, we need to go to MATLAB and then open a new Simulink. Here I have already opened a Simulink and I opened a blank model or canvas, so we can start from scratch to start building this model. So the first step says set the constant 12 Newton input force by using the step block from the sources. Set the step time to 0.02 and set the final value or magnitude to 12. So we need to go to our Simulink model, and here we should be able to resize this window so we can see the step. Okay, so here I'm going to go to, I can go to the library and choose the step, or I can double click on the canvas and choose step. So it says that this step is from the Simulink sources category. So I know that this is what I'm looking for. When I click on this, I see that this is the step size. Now the instruction says double click on the block. So this should bring in the properties window. Here says the step time should be 0.02. The initial value is 0, meaning what the value of the step would be before the step, and what would be the value of the input after the step time. So here, after the step time, we want it to be 12 or 12 newtons. We leave the sample time as 0, so it will be inherited from other blocks if necessary. And we'll click OK, so we're done with this block. Next, we have click or drag the transfer function icon from the continuous library. Set the system parameters by entering the transfer function numerator and denominator polynomials as row vector in descending powers of s. Once the values are applied, the block will show the transfer function with powers of s. Again, we can click on the library browser. We can go to continuous block and we can choose the transfer function and then drag and drop it. Or like what we did for the step function, we can just double click anywhere on the canvas and then just type transfer and it will bring us some of the options. And we can just click on the first one that is from Simulink continuous category. So now by default, we see how it looks. It has 1 over s plus 1. This is because by default, the numerator and denominator coefficients are set as 1 and 1 and 1. For this system, we need our transfer function to be what is in the equation. So we need to replicate this transfer function. So the numerator is going to be still 1, but the denominator will be ms squared. So m will be our first one. That will be 0.04. The next one will be the coefficient for s. So we need to use the b value. And the last one will be the k value, and that will be 7,000. So we leave everything else as is, and then we click OK. Now we see that when we do that, and I'm going to just zoom in so you can see how things look. As we do that, it shows us the numerator over denominator with the Laplace variable s. But if I try to expand the size of this block, and if it has enough room, it will actually show me the full fraction. So this is my transfer function for this system that we have been working on multiple times. So we can also double check if the transfer function is built properly. Again, this is for you to double check if you have input the coefficients for the denominator and numerator properly. So now that I have my input block and my system block, that is my transfer function, I can double click on the blocks to label variables and label block titles. So in this case, I don't want to do that. That is more for appearance. We need to also get a click or drag the to workspace icon from Sinks library. Double click on the to workspace block and set the variable names and set the save format to array. So this is to make sure that we can output our data to the workspace and then be able to plot our results from workspace. But before we do that, we want to be able to actually just see how the output is going to be for this. For that purpose, I'm going to add a scope. And now I'm going to connect all these blocks to one another. So my input block is connected to my transfer function block, and my transfer function block is connected to my scope. Now with this one, I should be able to run my simulation and get some results. So I'm going to run this simulation. Simulation was compiling, and if I click on my scope, I should be able to see my result. So I get my result. But this doesn't look quite right, or it at least looks somehow too condensed at the very beginning of my simulation. If I zoom in, I see that I basically need to only look at maybe 0.01 second in my simulation. So here at the stop time, I can change my simulation stop time to be 0.01 second. And if I run my simulation again, I will see nothing. So then I have to increase this. Okay, so with 0.01, I can see my simulation. And we see that we actually have at 0.02, we have an input. The input causes the system to react, so it will start to change its value. It overshoots above its settling value or set point. Then it comes back down, oscillates, and then gets to the set point. We also can see that we actually have still a coarse response, meaning that it's not refined, it is not smooth. And this is not really how the system should behave. This is because we have not changed any properties from the Simulink model to have indicated step sizes that are fine enough or small enough that give us a smooth trend line. Because we haven't, Simulink is deciding on that step size automatically, and that value, it seems, is not small enough for us to capture properly the behavior of this system output. To change that value, we can go to our Modeling tab, go to Model Settings, and this should bring in the Properties window. And in here we see that the solver selection has a variable step and it is set to auto. So here we need to change this to fix a step, and we need to choose, there we can just keep that as variable step, but we can change our maximum step size to be, instead of auto, to be 1e minus 4, a smaller value. And then this makes sure that our step size, even though variable, is never going to be bigger than this value. So if I click on this now, so I click OK to apply these settings, and then run my Simulink model again, now we see that we have a smoother trend line. So that was definitely the step size issue here. Now that we have seen our response in the scope, let's say we would like to save this setting or save our data to a variable, and then we would like to plot them in MATLAB. To do that, we need to go back to MATLAB. So this is the step size change step. This is step 5. We looked at the simulation, and we should be able to plot these values. But for that, we had to finish step 4. So to finish step 4, we need to create a 2 workspace. We see that by default the name is SimOut. We're going to change this to Y and change the save format to array. And then a 2D array. And we can create actually another one and then call this U as our input. So we just copy and paste it, the block. So we connect this to the input, and then we connect this to the output. Now with this, when we run our simulation, I'm going to open MATLAB here so we can see that we do have the out variable. And then when I run this, the out variable should have 2 values in it, U and Y, in addition to the time and other properties. So when I double click on that, I say I have the T out, that is my time, U and Y. So now having these, I should be able to plot these variables. So I'm going to start my code with CLC I'm not going to clear because that means I will lose my workspace variables. But I'm going to try to close all open figures if there are any, and if I'm going to run this multiple times, then I'm going to plot, but I want to see my input and my output. So I'm going to create a subplot. Two rows, one column, and in the first one, I'm going to plot out.tout and out.u. And then I can add grid, I can add X label, and Y label. And I'm going to copy paste, change this to be now the second plot in the subplot series, and I'm going to plot in this one the output and change this to output. So with this, I should be able to get a plot that shows my system output and my system input. So it says that I have a typo, should be X labels, then run it again. So we see that we get, again, the input and output below one another. We see that this is our input to the system. It's a step function at 0.02 seconds that goes to 12 newtons. And as it does, we see that our system responds with a behavior that is increasing in the amplitude of the output, overshooting over the set point, oscillating around the set point, and then settling at its stable point or stabilizing at a set point. So that is what the result is. This is creating a very simple model from the system that we have looked at multiple times and we have modeled before in Simulink. This time we used, in MATLAB, this time we used Simulink. And in Simulink, the first option that we had was using a transfer function. And doing this resulted in this type of figure for us. And we see that this is our output. And we also looked at the input. Now, the next example is giving us, again, the same system, but is asking us to, instead of using a transfer function, use a state space model to do the same thing for our system. So to be able to do that, we have to first put our system into state space form. We have the equations of motion. We substitute the values for the coefficients or system parameters. We have to choose our states, so we choose x1 for y, x2 for y dot, and input u for ft. With this, we can rewrite our equations, rearrange our main equation to obtain our x2 dot or y double dot, and then write all our equations in terms of our states, and then put them in the state space form. Doing that, we get our state space equations as x dot equals ax plus bu. So this gives us the A and the B matrices and vectors. And y would be, so our output is our position or displacement, which we defined as a state x1. So our y would be 1, 0, x1, x2. That is 1, y, 0, y dot. Plus, there's no input in our output, So 0 output. So our C matrix or C vector and the D matrix is equal to 0. Now to do this, what we need to do is instead of inputting the transfer function, we need to use the state space model function, and that block in Simulink has inputs A, B, C, D matrices. So if we input these matrices, we should be able to get the same result. Now what we're going to do to save some time here is we're going to work on the existing model that we have. So we're going to expand this. But as we expand this, we're going to add another block that is our state space block so that we can actually compare the result. So I'm going to start typing state space. So this is the state space from the continuous block. As you see, the face of this block is x dot equals ax plus bu and y equals cx plus du. The input to this block is our u, and then A, B, C, D matrices are properties of the block. So if I double click on this, it asks me what are the A, B, C, and D matrices. So I can input them from what I already have in the slide. So A matrix will be 0, 1, negative 1, 7, 5, 0, 0, 0, and negative 400. Note that we use a semicolon in vectors to define a new row in a matrix in MATLAB. For B, I have 0, 25. For C, I have 1, 0. And for D, I have 0. We leave the initial condition as nothing. It has a 0 initial condition. And we click OK. So now our state space block should be ready. We are going to input the same input that we had. And we would like to see the output. So to be able to compare the outputs, I'm going to change my scope to be able to accept 2 inputs. So number of inputs, I change it to 2. And I want them to be overlaid, so I don't change the layout. But I go to display and I activate show legend. Click OK. Now I have 2 inputs, and the second input for this system or this scope, I'm going to put it as the output of my state space model. Now in order for me to be able to differentiate my scope signals, I'm going to name the signals that are going to it. So this will be the transfer function output. This will be SSR output. Now if I run my simulation and check my scope, I can see that I should have 2 different outputs, but in fact, because they are overlapping, so they are exactly giving me the same output, I only see one line that is my SSR output. To double check this, or to confirm this, I can output my SSR output as y1 or y2, so this is now y1. If I run this, I should have this in my workspace. So if I go back to MATLAB, I check my out variable. Now I also have a y1 variable stored here. And now I can overlap this in my output. And then I can change the colors and the markers for these 2 plots. And then I need to add a legend as well here. So this is going to be transfer function, the first one, and the second one is going to be state space. Now if I plot this, it says that there is an issue. Okay, so the reason is this does not accept. Okay, that is because I missed a comma, so it should be this. So if we look at this, we see that because we have so many data points, we actually see a very thick boundary that is blue that is surrounding the red line. The blue is actually our transfer function markers that are so many that are showing similarly to a thick line that is following the red line or overlapping the red line. And the red line is the SSR, or our state space representation model. So if we were to zoom into these plots, we would actually see that they are fully overlapping. And that shows that the result we are getting from either the transfer function or the state space representation is the same thing. So we just need to add the state space model, input the matrices, and everything, all the other steps will be similar to the previous example. But what we did here, we tried to combine the two examples and then compare the outcomes, and we saw that they give us exactly the same output. So this is the state space block. And next we get to the integrator block. Note that with the transfer function approach, we cannot include initial conditions in the simulation due to the definition of the transfer function. Also, suppose that we wanted to compute and store the velocity of the mass. Remember, in here, we are only able to obtain the position. There are ways we could actually obtain the velocity as well, or y dot, but we would have to make some changes to our state space representation, and transfer function would be different. So if we wanted to get both at the same time, we could use the SSR and change our output formulation and then divide our outputs to two outputs. But we could also use the integrator block. So what we can use is the integrator block from the continuous library to integrate each derivative term. The integrator block method can also be used to simulate nonlinear systems, which means this approach is more flexible than the transfer function and the state space representations. So we have more abilities, more flexibility with the integrator block approach for system modeling in Simulink. Recall the mechanical systems dynamic. So we looked at the system model that my double dot plus by dot plus ky equals f. Because the model is of second order, we have the y dot, so the second differential equation. We need two integrators. The first integrator will integrate y double dot and produce y dot. And the second integrator will integrate velocity y dot and will produce position y. So for the integrator block, if we input a derivative, it will give us the output as an integral of that derivative. So if we have y double dot, we will get y dot. If we have y dot, we will get y. But in integrator block, you also can include or add initial conditions for that integration. So in our case, it will allow us to include initial conditions for our system modeling. We can set initial conditions for velocity and position by double-clicking the respective integrator blocks. So again, we go back to the same system, but this time we would like to use the integrator block approach to model this system. So we have our xy dot and x2 dot as y dot and y double dot. So these will be our two differential equations. And we should be able to use this integrator block to be able to integrate our terms and obtain our outputs. Now note that in this one, because we do not have a transfer function or the state space representation, we actually have to build these equations for ourselves. So the y dot is just an integral of y double dot, but y double dot has the y dot and y and the input in it. So we have to create in Simulink this term in such a way that we are able to integrate or input to our integrator block and then integrate to be able to obtain our final result. So to do that, we are going to follow the same thing that we have been doing. So we are going to try to add that or these equations to the model that we have. And to do so, we need to basically create this equation. So we first need a sum block. So this is going to be our sum block. So note that we have to create this term. The first addition in this term is ft. So we need to add our input. To make it more understandable, we are going to double click this. In this case, we need, I think, 4 inputs. And we make it a rectangular representation. So we're going to resize this. Our first input is going to be plus ft. So we are inputting our input ft as a plus. Next we have minus 7,000y, but we don't have the y. So where do we get the y? That is the question. To be able to obtain y, we need to first form y double dot, integrate get y dot, and then integrate and get y. So we're going to add 2 integrator blocks. And to form this, we know that whatever goes out of this summation needs to be divided by 0.04. So in here, we need a gain or a multiplier, but we're going to use a gain. And then put this gain as 1 over 0.04. We can expand this to actually show the value. And this multiplied will be this term multiplied by 1 over 0.04, and that will give us the y double dot. And then integrating the y double dot, we should be able to get y dot. I'm just going to name these signals y dot, y double dot. And then from here, we have also y, which we will call integrator output. And to be able to check everything, I'm going to just change this to have now 3 inputs. And then add the third input to be the integrator output approach. Now, we also know that this is equal to y. So this y needs to be multiplied by 7,000 and then subtracted from this full summation. So to be able to multiply that, I need a gain block. So I'm going to get 2 gain blocks, one for y dot. For the y dot, I can put negative 7,000 and for the y dot, it is going to be negative 16. Now I can also change the direction of these by right-clicking them and then format and then say flip block. And then I will have my output y multiplied by negative 7,000 and then added to the summation, and then my y dot multiplied by negative 16 and then added to the summation. So this only has 3 terms, which means I can get rid of my last summation. So I only have 3. One is my input ft, one is negative 7,000 y, and one is negative 16 y dot. When this term is created, I multiply it by 1 over 0.04, and that is sent into the integrator block. From the integrator block, the y dot is produced. The y dot goes to another integrator block, and the output of that will be my y output. So if I run this, I should now have 3 different results. And I should see that my 3 different results again exactly overlap. And that gives me this one line that is now red because we added the integrator output. So it is overlapping both transfer function and a state space representation outputs. So we used 3 approaches to obtain the output of this system that we were able to find the system model for, put in different forms, use transfer function, use a state space representation, and use the integrator block to be able to get our system output. If we want to, we can also add another output here. We call it output 2 to send that and store it into workspace. Once we do that, we can go back to MATLAB and then add that as another input. So we want to have this as green color, and if we run this, actually we have to add another legend. If we run this, we would get a new plot, and we see that now this time it is green, but if we were to zoom in, we see that we do have the triangles, we have the circles, and then we should have the red line as well. And that basically shows, again, that all three methods are giving us the same output. So let's see what else we can do. So we created this Simulink block and we were able to obtain the same result as the two other approaches. The transfer function approach is likely the most concise and easiest method to use. However, by definition, a transfer function cannot be used when the system has non-zero initial conditions. The state space approach is concise, but it requires the user to derive the complete state space representation matrices. However, it is flexible since it allows the user to set arbitrary initial conditions for all n states. The integrator block approach is likely the most flexible method, since it allows the user to set arbitrary initial conditions for all dynamic variables, plus the user can store and plot any signal path variable, which may aid in troubleshooting complex simulations. So again, what we could also do in the integrator block approach was we could actually see not only our output y, but also our y dot. So if we run the simulation again and look at this scope this time, we could see that we do have both the integrator block. So I'm just going to remove one of the outputs. And I'm going to change the layout to show them top of one another instead of overlapping them. Then run the simulation again. So with this, we can see that we have the integrator block, that is our y, and then we have the y dot. So we can also individually see each integrated system state that we were not able to see directly in our state space representation and in our transfer function approaches. Next, we focused on using Simulink to simulate systems that are governed by nonlinear mathematical models. Numerical simulation methods are likely the only option available for obtaining the dynamic response of nonlinear systems, whereas analytical techniques can be used to obtain the solution for linear systems, such as the second-order mechanical system. It is important to remember that we cannot use transfer functions or an SSR when dealing with nonlinear systems. Our only option is to use numerical integration of each nonlinear ordinary differential equation, which we perform using Simulink and the integrator block approach. So consider again the spool valve system in the examples we looked at, but with the inclusion of the column or dry friction. We mentioned before that the column or dry friction will add nonlinearity to our system equations, along with viscous friction. Simulate the response to a 12 Newton step input. So what this changes this time is we have additional term, that is the column or dry friction, which is nonlinear and makes our equations nonlinear. So it forces us to use the integrator block approach. Considering the case where friction is modeled by column or dry friction plus viscous friction, so we already have the by dot, but we want to add the column friction as well, or the dry friction, which is a nonlinear term. Therefore, a certain amount of force must be present to overcome dry friction force F dry, and the total friction on the mass is the column dry friction plus viscous friction. So this makes us have an additional term here that is F dry sine y dot. Dry friction is a nonlinear effect, and it can be modeled using the sinem or sine function. The mass spring damper model is repeated with the column plus viscous friction, and in this case we have the F dry to be equal to 0.4 newtons. So we replace the F dry with 0.4 newtons multiplied by the sinum or sine of y dot, which is the velocity. So this will be now our full equation for our system. So having this, what we need to add in our integrator block is an additional term for the nonlinearity. This will result in an additional route from the y dot, and then a new block that is a sine block, and then adding that to our summation that will basically result in our y double dot. So if we move things around here, if you remember from the equation we looked at earlier, we will have an additional term here that is minus f dry sine of y dot. So if we go back to Simulink and we try to expand on what we already have built, we can add or copy paste all these blocks here. And then try to build on top of that. So here we will have our input as the same input. Now we have an additional term, so we need to add the fourth block. And again, it is the y dot, so it is going to be a y dot multiplied by a -4 So the y dot, we need to add a new route. This will be -0.4. But we also need the sine, so we're going to use the sine function. We see how the sine looks. We need to flip it. So it goes to a sine. So y double dot will go to a sine. We get sine of y dot. Goes to the sine. We get sine of y dot. Then it's multiplied by -0.4 and then added to our summation. So this will now give us the nonlinear model. So now we change this. So this will be integrate linear. We call this integrator output nonlinear. Then we go to our scope. We add the fourth input. And then we add the fourth input as the integrator nonlinear, and then we run our model. So we were facing some issues with the MATLAB graphics. So we had to restart MATLAB. We are back again. And if we run our simulation, we see that because of the nonlinearity, it is taking a little bit more time. And once we check on the scope, we see that all the other models that didn't have the nonlinearity are behaving differently than the model that has the nonlinearity. So we see that the nonlinearity is adding a difference in the behavior of our system. Now the next topic is how can we use integrated system or model integrated systems in Simulink? Clean method for constructing complex simulation can be used to build integrated system or systems of different types that have different type systems or different portions of the system like we have discussed that are, for example, electromechanical system or hydromechanical system or system of that sort that have different portions having a core different type of system. So we can interconnect them and then have a universal or a final system model. The basic idea is to create each subsystem separately using Simulink and then build a subsystem by enclosing with bounding box or use subsystem block from ports and subsystems library. So the idea is if you have subsystem 1, subsystem 2, and subsystem 3, and they are interacting with one another, you can create each individually as a subsystem and then have their inputs and outputs feeding one another so that you can have your overall system working as expected. This example will try to tackle that kind of approach. A solenoid actuator valve system, which is an electromechanical system, is shown in this picture. Construct an integrated model using Simulink and determine the response of the solenoid coil, current I, and the valve position X for a 10-volt constant voltage input applied at time t equals 0.05 seconds. The system has zero stored energy at time 0, which means the system has 0 initial conditions. So for this, we first have to model our system. We have two subsystems, electrical part and the mechanical part. The electrical part is an RL circuit. The mechanical part is a mass spring damper system. We have seen both of these before, so it should be pretty quick to model each. So for the solenoid coil, the electrical part, the system model will be Li dot plus Ri equals E in minus Kix dot. And for mechanical part, we have Mx double dot plus Bx dot plus F dry sin x dot plus Kx equals Fem. And we have Fem as half Ki squared. So we see that the mechanical and electrical part are interconnected as the electrical part has x dot from the mechanical part, and the mechanical part has I from the electrical part in their respective equations. Now we have to individually model the electrical part and the mechanical part. We can use all the techniques that we have seen so far to be able to build these individual models from the equations that we have looked at. The only difference would be these input and output blocks that now will exist in the individual subsystem blocks. So for the solenoid system or the electrical part, when we create this model, the input to this system will be E in and X dot. The X dot should come from the mechanical part, and its output will be Fem. The Fem will go to the mechanical subsystem. So for the electrical subsystem, the two inputs are E in and X dot, and the output is Fem. Now for the mechanical part, which we already created, and we saw that is the mechanical part with the nonlinearity term, the dry friction force. Now we treat it as a subsystem of a bigger system, which is the electromechanical system. And for this subsystem, the input will be Fem from the electrical subsystem, and its output will be X and X dot, when X dot goes back to the electrical part as an input. So looking at the mechanical part as a subsystem, it has one input, Fem, and two outputs, X and X dot. So if we were to put these together as two subsystems interacting with one another. We would have an input system, an input to the full system, that is our voltage. The voltage goes to the electrical subsystem as an input. It works and gives us the FEM. The FEM goes to the mechanical part. The mechanical part gives us x and x dot, position and velocity. The velocity or x dot has to go back to the electrical subsystem as input, and this loop continues so that we get the output, position, and velocity for this system. And we can also get I, which is the current in the electrical subsystem, as an output as well, if we wish. So here it is asking us to determine the response of the solenoid coil current and the valve position X. So we actually would need to get the current from the electrical part as well, which we could easily get as an output. Here I, we are able to output it to workspace. If we wish to plot it in a scope, we can also output it as an output from the subsystem. So for this example, we also have all the information for individual elements in this subsystem as given in this table, so we can input them. And to be able to input them, we can write a script that stores these values in the workspace, and then we can run our system model and then obtain the results directly using the sim function. And then we can use whatever values is stored in the workspace from the simulation running and then plot the information out. Now if we go back to MATLAB, I've already done the script for this sample. So we have the script sectionalized. And then before we run the script, I'm going to open the Simulink model and we're going to take a look. So here we see that we have the step block that is our input. We have the electrical subsystem and the mechanical subsystem. And the way you can insert subsystems, as we discussed before, is in the modeling tab. You can click on, in the component section, you can click insert subsystem. So it will create a subsystem for you that by default has one input and one output. To change whatever is inside this, you can copy the inputs. So you have multiple inputs and multiple outputs. So if I go back to my system, now this subsystem has two inputs and two outputs. So this is how you can create the subsystems. I have already done this for the electrical subsystem. If I go in, we see that this is created as such using the equations that we found. And all these elements can be found in MATLAB. So this is a product block. This is a math function. And you can try to find these blocks and work with them to create the equations for your system. The mechanical part we already created in the previous examples. So I leave this to you to do it on your own and create the electrical subsystem. And we also have these two workspace blocks that allows us to store, after the simulation is run, the outputs in the out variable or structure in the workspace so we can use them for plotting. Taking a look at the mechanical subsystem, we also see some of these blocks that are highlighted with a red color. This means that these have coefficients or values that are not already defined. When we run our script and these values are loaded, these variables are loaded in workspace. So I'm going to go ahead and run the first section here, load these variables in the workspace. And if I go back, we should see that all those red highlights would disappear because now Simulink can find those values in the simulation. So now that we see the simulation, this time we are going to, and we save it as example 6.9, and it's in the same folder as our script. So this means that we can use the sim function to be able to store the output of the sim function into the out variable, and then use the out variable outputs to plot our information. So the sim gets the name of a Simulink file with its path. If it is in the same directory as your script, you can just give the file name. You don't have to give a path. So here they are in the same folder directory. So we're only giving the file name of our Simulink model. And with this, we save the output of this simulation into the out variable. So I'm just going to clear my workspace, run the first section to load the variable so I don't have out anymore. Next, I'm going to run the Simulink and store the outputs that are the storages to workspace into out variable. So now we see that the out variable is created. Now it does have FEM, I, T, T out. So T and T out are the same. We don't have to store T out, T, because by default out does that. X and X dot. So X is our position, that is one of the output we need, and I is the other, the current, that is the other output we need. Now that we have all of these stored, we should be able to plot our X and our I. We can plot them in two different figures. That is how it's done here. So I'm going to run this section. We see the current and we see the XT. So we get two separate plots. We see that when the input changes, the system outputs I and X also change differently. And if we were to actually try to plot these similar to what we have done in the past, we can make a small change in our Simulink model so that we can actually store our input in a variable as well. So we call this U, similar to the previous examples. Save this. And go back to our system. So here, instead of having two different figures, we're going to do subplot, and this time 3 subplots. In the first one, we're going to plot our input. So this will be our input. Then we have our X, and then we have our, but we need to add the subplots. So this one will be 2, and this one will be 3. So this way, we run the simulation again, so it also stores our input. Once that is done, if we run this, we get now a figure with 3 plots or subplots. So we see that as our input is changing, our output for position and for current also change. Something that can be seen here is that because of the step size that we have, we get the step to look like a ramp. So if we go back to our system modeling, and then we go to setup, we see that the step size is 0.01. So we change this to 0.001. And then save, and then run the simulation again, and then plot the results again. And we should see this time that because of the finer time steps that we have, we are getting an actual step instead of a ramp for our input. So this is always good to check your inputs, outputs, and plot them this way so you can see the changes, you can see if the behavior is as you're expecting, or if not, what you can do to fix it. And in general, a good way to communicate your result to your audience. So this is the output we should get for our X or position and I or current. And this would be the end of this tutorial for examples of applications of Simulink for control purposes.